The construction of Zim-Samy represents a highly coordinated feat of modern shipbuilding, where logistics and large-scale assembly play a decisive role in meeting demanding schedules and precision standards. Long before the hull took shape in dry dock, steel blocks were fabricated in parallel at multiple workshops. Each block, some weighing several hundred tons, was outfitted in advance with structural reinforcements, piping, cable trays, and foundations. This high level of pre-outfitting significantly reduced time spent working at height and inside confined spaces during final assembly. Once completed, the blocks were transferred from fabrication halls using self-propelled modular transporters. These multi-axle platforms enabled slow, millimeter-accurate movement across the yard, maintaining strict alignment tolerances. For waterfront transfer, gantry cranes and heavy lift cranes lifted the blocks onto transport barges or directly into the dry dock, depending on sequence and weather conditions. Block installation followed a carefully engineered erection plan. Lower hull sections were positioned first, forming the structural backbone of the vessel. As assembly progressed upward, midship and engine room blocks were installed, followed by accommodation and deckhouse units. Each lift required real-time coordination between crane operators, rigging teams, surveyors, and welding crews to ensure correct geometry and stress distribution. Temporary alignment aids and laser measurement systems were used to verify positioning before final welding. Once secured, internal connections between blocks, structural joints, piping systems, and electrical networks were completed rapidly thanks to the high degree of pre-integration. The superstructure and deck blocks were installed in later stages, often as large, fully assembled units. This modular approach minimized rework and allowed parallel progress across multiple trades. Through disciplined logistics, synchronized transportation, and precision block assembly, Zim-Samy moved efficiently from steel sections to a fully formed container vessel. The project demonstrates how modern shipbuilding relies not only on engineering strength, but on the flawless orchestration of movement, timing, and assembly at an industrial scale. COSCO Shipping Taurus stands among the largest container vessels ever constructed, stretching 399.82 meters in length with an extreme breadth of 58.72 meters. Delivered in 2018, the ship has a gross tonnage of approximately 199,000 and a deadweight of 197,500 tons, with a nominal capacity of up to 20,000 TEU. On May 16, 2018, COSCO shipping tourists arrived at the port of Piraeus, marking a significant moment for one of the Mediterranean's key transshipment hubs. Designed for ultra-large container operations, the vessel integrates high-efficiency propulsion, optimized hull lines, and advanced cargo management systems to maximize slot utilization and reduce fuel consumption per transported unit. Its scale reflects the industry's continued pursuit of economies of scale on major east-west trade routes. The arrival of Maersk Mumbai reflects the scale and complexity of modern container shipping. As an ultra-large container vessel designed for long-haul international trade routes, the ship is built to handle massive container volumes with optimized slot utilization and advanced stability systems. Its design integrates fuel-efficient main engines, optimized hull geometry, and digital navigation support to reduce emissions and improve operational performance. During port calls, vessels of this class require precise berth allocation, high-capacity quay cranes, and tightly coordinated yard logistics. The successful handling of Maersk Mumbai at Tanger Med illustrates how shipping line, port authority, and terminal operator align vessel scheduling, crane productivity, and landside operations to achieve efficient turnaround and maintain global supply chain continuity. Navantia Reparaciones Cadiz San Fernando operates as a highly specialized hub for large-scale cruise ship repair and modernization, where complex engineering, logistics, and tight schedules converge. The refit of Allure of the Seas, one of Royal Caribbean's Oasis-class vessels, illustrates the shipyard's technical depth and operational discipline. The project began with detailed planning and interface engineering, coordinating dry dock availability, material flow, and multi-trade access across the vessel's extensive systems. With an overall displacement exceeding 220,000 gross tons, docking operations required precise ballast control, continuous monitoring of hull stresses, and strict alignment tolerances within the dry dock. Hull works focused on underwater inspections, steel repairs, and advanced surface preparation. High-pressure hydroblasting was applied to remove old coatings, followed by the application of modern anti-corrosive and anti-fouling systems designed to reduce hydrodynamic resistance and fuel consumption. Coating thickness, curing times, and environmental conditions were closely controlled to meet class and manufacturer specifications. Propulsion and maneuvering systems formed another critical work package. Azimuthing pods, stabilizers, and thrusters were inspected, overhauled, and realigned. Bearing clearances, seal integrity, and lubrication systems were verified to ensure long-term reliability. Where required, components were removed using synchronized lifting plans involving fixed cranes and mobile heavy lift units operating within confined dockside geometry. Mechanical and auxiliary systems underwent parallel upgrades. Sea chests, overboard valves, and cooling circuits were dismantled, cleaned, and pressure tested. Tank inspections included structural surveys, coating repairs, and cleaning operations, compliant with environmental regulations. Electrical and automation teams addressed power distribution, sensor calibration, and redundancy checks to support the vessel's hotel load and safety systems. Navantia's prefabrication capabilities played a key role in schedule control. Structural elements, Piping modules and aluminum blocks were manufactured offline, pre-outfitted, and installed as complete units. This modular approach minimized onboard hot work and reduced interface risks. Lifting operations for large blocks were executed under strict load control procedures, with real-time monitoring to protect both structure and personnel. Environmental management remained integral throughout the project. Dedicated systems handled gray and black water treatment, oily waste, and blasting residues. Continuous monitoring ensured compliance with international standards while allowing essential onboard services, such as air conditioning, fire protection, and machinery cooling, to remain operational during the refit. Through disciplined project management, round-the-clock operations, and coordinated use of shared facilities across the Cadiz shipyards, Navantia delivered a technically complex refit within demanding time constraints. The Allure of the Seas project demonstrates how large cruise ship repairs depend not on isolated tasks, but on the precise integration of engineering, logistics, and execution at scale. A remarkable heavy lift operation unfolded in the Walhaven as a special breakbulk cargo arrived on site. The transport involved 14 inland barges, working in coordination with 4 floating cranes to position and handle the oversized structure. Measuring 135 meters in length and 17.5 meters in width, the cargo weighed more than 1,800 tons. Such dimensions required precise lifting calculations, synchronized crane movements, and careful ballast control to ensure stability throughout the operation. The project demonstrated the port's capacity for complex maritime logistics, where scale, timing, and engineering discipline converge to manage exceptional cargo safely and efficiently. On the 28th of February 2025, MV Vissersbank was launched using a controlled sideways slipway method, selected to optimize structural stability and yard efficiency. After final buoyancy checks, the hull entered the water smoothly under gravity. The ceremony marked the transition from construction to outfitting and sea trials. Snow settles across the hulls and gantry cranes, transforming the shipyard into a quiet industrial landscape. Steel structures stand against the white horizon as maintenance, outfitting, and fabrication continue despite freezing conditions. Even under snow, precision work advances, proof that shipbuilding never truly pauses. The Olympic Trophy stands as a benchmark project in modern ship conversion, demonstrating how engineering precision and disciplined execution can transform scale and purpose in record time. Originally built as a very large ore carrier, the vessel underwent a full conversion to a very large crude carrier in just 51 days, an exceptional achievement by any shipyard standard. Executed at Oman Dry Dock Company's shipyard in Duqm, the project required extensive structural, mechanical, and systems modifications. Cargo holds were reconfigured into compliant oil tanks, including the installation of new bulkheads, strengthening structures, and coating systems suitable for crude oil service. Piping networks, pumping systems, and cargo handling arrangements were redesigned to meet large ore carrier operational requirements, while stability, longitudinal strength, and global hull integrity were carefully recalculated and verified. Parallel workflows, round-the-clock operations, and precise coordination between engineering, production, and quality control teams were critical to meeting the compressed schedule. In just 51 days, a bulk carrier was reborn as a fully operational crude oil tanker, efficient, compliant, and ready for global trade. Using the Ortson 500, ship hull cleaning removes marine growth, old coatings, and contaminants with high-pressure water jets. The process prepares steel surfaces for anti-corrosion treatment, improves coating adhesion, reduces drag, and extends hull service life, while minimizing abrasive damage and environmental impact during dry dock maintenance operations worldwide safely. Eco-friendly blasting reaches a new standard with the VertiDrive V400, a closed-loop robotic system engineered for sustainable industrial cleaning. Designed for vertical and overhead surfaces, the V400 combines ultra-high-pressure water blasting with an integrated vacuum recovery system. During operation, wastewater contaminated with coatings, tank liners, and corrosion byproducts is captured immediately at the blasting head, preventing dispersion into the air or surrounding water. Unlike conventional blasting methods that release abrasives and pollutants into the environment, the VertiDrive V400 operates as a controlled process, significantly reducing secondary contamination, airborne particles, and cleanup requirements. This approach improves worker safety while ensuring compliance with increasingly strict environmental regulations. By minimizing waste, lowering water consumption, and reducing the need for containment infrastructure, the V400 helps shipyards, tank terminals, and industrial contractors cut operational emissions and overall carbon footprint. The result is a cleaner, surface preparation process that aligns high-performance cleaning with long-term environmental responsibility. Ship hull blasting enters a new era with this abrasive and water blasting robot. A magnetic, semi-automatic crawler, it performs both high-pressure cleaning and ultra-high-pressure paint stripping. Tested in a shipyard environment, it handles mega yachts with ease, operating vertically or upside down, adhering securely with powerful permanent magnets. VertiDrive's V700 abrasive blasting robot demonstrates precision and productivity through its advanced triple-nozzle configuration. Operating directly on the ship hull, the magnetic crawler maintains constant adhesion while distributing blasting energy evenly across the surface. This setup increases coverage rates, ensures uniform coating removal, and reduces passes. Designed for demanding shipyard conditions, the V700 delivers controlled, Dry docking is a critical phase in a vessel's life cycle, providing full access to underwater structures that cannot be inspected or serviced while afloat. During this operation, the ship is carefully positioned in a dry dock, water is drained, and the hull rests on keel and bilge blocks, creating a stable environment for comprehensive inspection, repair, and reconditioning. Once dry, hull maintenance begins with the removal of marine growth, such as algae and barnacles, using high-pressure water jetting or abrasive blasting. The exposed steel surface is then inspected for corrosion, deformation, or cracking. Damaged areas are repaired as required, followed by the application of anti-corrosive primers and anti-fouling coatings to protect the hull and optimize hydrodynamic performance. Critical underwater components receive close attention. Sea chests, overboard discharges, and seawater suction valves are dismantled, overhauled, and pressure tested. The rudder, carrier ring, and steering gear connections are inspected for wear and alignment. Tail shaft bearing clearances are measured, and where necessary, the tail shaft is withdrawn for detailed examination of bearings, seals, and journals. Internal spaces are addressed in parallel. Ballast, fuel, and cargo tanks are cleaned, ventilated, and surveyed for structural integrity and coating condition. Shipside gratings are removed, cleaned, repaired, and reinstalled. Locking devices and hull penetrations are checked to ensure proper clearances and watertight integrity. Anchor chains are ranged out, cleaned, gauged, and remarked according to classification requirements. Throughout the dry docking period, inspections are conducted in coordination with class surveyors to verify compliance with regulatory standards. The dry dock process restores structural integrity, extends service life, and ensures the vessel returns to operation in a safe, efficient, and fully certified condition. Under growing efficiency pressure, cargo hold cleaning must be fast, safe, and fully compliant. Dock cargo hold cleaning demands precision, speed, and regulatory compliance. Advanced, high-pressure systems, combined with engineered chemicals, enable faster residue removal, reduced manual labor, and safer operations. Modular, reusable equipment improves maneuverability, shortens port stays, and ensures consistent cleaning performance across rapid cargo changeovers. On Christmas Eve 2016, the general cargo vessel Cabrera ran aground on the rocky coastline of Andros, Greece. Exposed to heavy seas, the hull fractured, and the vessel ultimately sank to a depth of approximately 34 meters. The incident posed both navigational and environmental risks in the Aegean. SMIT Salvage, in cooperation with Greek partner Megatugs, responded rapidly. The initial phase focused on pollution control, including the safe removal of bunker oil and the recovery of accessible cargo. Following stabilization, the consortium secured the contract for full wreck removal. The operation centered on lifting the stern section, including the accommodation block, along with remaining cargo from the seabed. Boskalis deployed the floating shear leg crane Toklift 4, providing the heavy lift capacity required for precise subsea recovery. In October 2017, after detailed engineering and controlled lifting procedures, the wreck section was successfully removed, restoring safety to the surrounding waters. The removal of JBB Durong 19 unfolds as a precisely coordinated salvage operation. A 1,000-ton shear legs crane, Smith Cyclone, is mobilized alongside specialized recovery equipment. At site, the wreck's bow is carefully lowered onto the seabed, stabilizing the structure for controlled cutting. Engineers divide the hull into 5 calculated sections. Each segment is lifted methodically and transferred onto waiting scrap barges. The first barge departs carrying 2 sections. The second follows with the remaining 3. Every lift is executed under strict load control and marine safety supervision. Once recovery is complete, Smit Cyclone and the salvage spread are demobilized and returned to the Smit yard, bringing the complex wreck removal campaign. When a massive steel structure disappears beneath the surface, the challenge that follows is not only maritime, but deeply engineering-driven. After months of detailed planning, structural analysis, and site preparation, Resolve Salvage and Fire Americas undertook one of the most demanding recovery operations ever executed in the Americas. Rather than sectioning the hull, engineers chose a single-piece recovery as the most environmentally responsible method. Heavy rigging was installed beneath the submerged wreck, and Resolve deployed its patented heave-compensated chain puller system from the Conquest MB-11 400-ton derrick barge and RMG 302 crane barge. After meticulous alignment and load preparation, the DB-1 was lifted steadily with approximately 6,000 tons of lift force, an unprecedented achievement for the region. The successful recovery stands as a clear demonstration of advanced salvage engineering, operational discipline, and the ability to solve complex offshore problems where margin for error is minimal and precision defines success. The wreck removal of the fishing vessel Almadraba Uno demonstrates a pragmatic and controlled approach to complex salvage operations. Located off the African coast, the vessel's condition and position made conventional refloating impractical. Structural damage, prolonged exposure to the marine environment, and limited lifting margins required an alternative strategy focused on safety and efficiency. A floating crane was mobilized and towed out to sea, positioning directly above the wreck site. This offshore deployment allowed heavy lifting operations to be carried out safely, away from the shoreline and unstable waters. Once secured, the crane provided the necessary reach and lifting capacity to handle segmented recovery. Instead of forcing a full salvage, the vessel was systematically cut into smaller sections underwater. Each cut reduced structural stress and allowed precise lifting. One by one, the sections were hoisted from the seabed and transferred onto barges for transport. This method minimized environmental risk, reduced uncontrolled movement, and ensured safe handling of the wreckage. By bringing the crane offshore, the operation gained flexibility and stability, even in challenging sea conditions. The operation demonstrates how modern salvage relies on mobility, precision, and realistic decision-making. Sometimes, controlled dismantling at sea is the safest and most efficient path to complete wreck removal. Off the rugged southwestern coast of Italy, a grounded vessel became the center of one of the most demanding wreck removal operations in the Mediterranean. Stranded in ballast condition and exposed to constant wave action, the ship faced progressive structural damage with every passing day. Resolve Marine was tasked with the operation, bringing experience forged in some of the world's harshest maritime environments. The response began with the mobilization of the crane barge from Gibraltar, a critical asset capable of handling extreme loads offshore. Once on site, the wreck was methodically cut down to the waterline, separating bow and stern with precise, controlled operations. Powerful chain pullers were then used to draw the stern section into shallower water, allowing further dismantling under safer conditions. Progress, however, was interrupted by unseasonably severe weather. Operations were suspended, and the bow's double bottom was deliberately left submerged through the winter to maintain stability. When conditions improved, the salvage team returned with renewed focus. Working alongside local partners, the remaining sections were lifted, transported, and dismantled. More than 3,000 metric tons of steel were recovered and responsibly scrapped in Piombino. What remained was not wreckage, but a clear coastline and a demonstration of disciplined, adaptive marine salvage under real-world constraints. Six kilometers off the coast of Eastbourne, a historic offshore landmark entered a carefully planned new chapter. The Royal Sovereign Lighthouse, commissioned by Trinity House for decommissioning, was scheduled to be removed in two controlled phases, beginning with the extraction of its accommodation unit and upper structures. Mobilization started at Shore Port, where the 1,000-ton jack-up barge Haven Sea Challenger was prepared with crew facilities and towed offshore by support tugs. The first objective focused on removing the iconic lantern tower known as the Pepper Pot. Using a 400-ton crane mounted on the jack-up barge, the structure was cut free from the deck and lifted intact before being transported back to port for reuse in a maritime visitor center. Following this phase, the heavy lift vessel Gulliver was mobilized to remove the lighthouse's top deck. Prior to lifting, extensive preparatory works were completed, including installation of lifting frames, supports, and temporary stabilizing tendons to ensure structural integrity during separation. With a lifting capacity of 4,000 tons, the DP2 equipped vessel provided ample margin for the estimated 1,000-ton topside. Strong tidal currents and variable weather required careful station keeping using anchors and continuous motion monitoring. Once conditions allowed, horizontal wire cutting was completed, rigging was tensioned, and the topside was lifted with precise control. The structure was then transferred onto a flat-top barge and transported to Shore Port for demolition and material recycling. The operation demonstrated meticulous offshore engineering, heavy lift precision, and coordinated logistics, ensuring the safe removal of a historic structure while preparing the site for the next decommissioning phase. Star of the Seas is a next-generation Icon-class cruise ship built for scale and efficiency. Powered by LNG dual-fuel engines, it combines advanced propulsion, optimized hull design, and integrated energy systems. With over 250,000 gross tons, the vessel represents a major step in sustainable cruise engineering and high-capacity maritime design. As vessel dimensions increase in the port of Rotterdam, propeller wash moves closer to the seabed, generating high-velocity jets that can cause severe scour. This pilot project investigates propeller-induced flow-through field measurements in Rotterdam and Ghent, combined with Deltara's model validation. The objective is to refine seabed protection design, safeguard quay wall stability, and enable larger vessels to berth safely at existing and future terminals. From highway logistics to maritime engineering, the transportation segment integrates infrastructure, vessel design, and operational discipline to move large consignments of cattle safely across international waters. The transportation phase defines the efficiency and integrity of the live cattle export chain. Movement begins with purpose-built livestock road trains, engineered for long-distance hauling. These multi-deck trailers feature non-slip flooring, reinforced partitions, and cross-ventilation systems to maintain airflow during transit. Stocking densities are calculated according to regulatory standards, balancing animal welfare with transport efficiency. At the port, trucks are sequenced to minimize holding time. Cattle are directed through enclosed raceways and gradually guided up hydraulic loading ramps that connect directly to the vessel's internal decks. This controlled flow reduces stress and prevents bottlenecks in high-volume operations. Once aboard the livestock carrier, transport shifts from road to sea. Animals are secured within ventilated steel pens arranged across multiple decks. High-capacity mechanical ventilation maintains air exchange, while automated watering and feed distribution systems support continuous care during the voyage. Environmental parameters, temperature, humidity, and airflow are constantly monitored to ensure stable transport conditions. At Fremantleport, the live export process begins long before the vessel departs. Sheep are carefully mustered and guided into livestock trucks, where each load is weighed to ensure compliance with transport and welfare regulations. Ventilated trailers maintain airflow during the short transfer from holding yards to the terminal. Upon arrival at the quay, the animals are directed through enclosed loading ramps and onto a purpose-built livestock carrier. Inside the vessel, pens are arranged across multiple decks, with controlled ventilation and monitored water supply systems. Automated feeding equipment distributes measured rations evenly, reducing waste and ensuring consistent nutrition throughout the voyage. Each stage, preparation, transport, weighing, and shipboard loading, follows strict operational protocols designed to maintain animal condition and logistical efficiency before departure from Fremantle. Shuttle revision under the Endurance program represents a systematic approach to extending the operational life of marine propulsion systems while maintaining original performance standards. The process focuses on comprehensive inspection, disassembly, and refurbishment of key shuttle components, including propeller blades, hubs, shafts, seals, bearings, and gear interfaces. Each element is assessed for wear, fatigue, and corrosion, resulting from long-term exposure to high loads and harsh marine environments. A central feature of the endurance revision concept is the application of advanced surface treatment and coating technologies. Critical components are rebuilt using high-strength materials and protective layers designed to resist abrasion, cavitation erosion, and corrosion. Machining tolerances are restored to factory specifications, ensuring precise alignment and efficient power transmission once reassembled. Throughout the revision, detailed testing procedures are carried out to verify mechanical integrity and hydrodynamic performance. This includes non-destructive testing, dimensional checks, and functional trials before final delivery. By combining proven shuttle engineering with modern refurbishment techniques, endurance revisions reduce lifecycle costs, minimize unplanned downtime, and significantly extend service intervals. The result is a propulsion unit ready to return to operation with renewed reliability, efficiency, and long-term durability in demanding maritime applications. The diesel engine assembly process at unit bow is carried out under strict technical standards, with a strong focus on precision, durability, and long-term operational reliability. Each project starts with the preparation of the engine block, where mating surfaces are inspected for dimensional accuracy, flatness, and concentricity. The crankshaft, bearings, and pistons are installed in a carefully controlled sequence to ensure correct clearances capable of withstanding high loads and combustion pressures. Attention then shifts to the installation of the valve train, cylinder head, and fuel injection system, where injection timing and combustion chamber sealing directly influence efficiency and performance. Auxiliary systems such as lubrication, cooling, and turbocharging are integrated to optimize thermal control and mechanical stability. Before delivery, every unit bow diesel engine undergoes comprehensive testing and fine-tuning, with key parameters monitored to confirm readiness for heavy industrial and marine applications. The assembly of the marine diesel engine reflects the advanced engineering standards of Japan Engine Corporation. The process begins with the precise placement of the bed plate, which forms the structural foundation of the engine and ensures long-term alignment under heavy operational loads. Next, the crankshaft is carefully inserted, aligned, and measured to meet strict tolerances critical for smooth power transmission. Following this, columns are assembled onto the bed plate, creating the main engine frame. The connecting rods are then installed, linking the crankshaft to the piston system. Jacket block assembling follows, integrating cooling passages designed to manage the high thermal loads generated by the 500 mm bore and two 300 mm stroke. The piston rods are mounted with careful attention to clearances and surface finish, ensuring reliability at an output of 780 kilowatts per cylinder. Cylinder covers are assembled next, incorporating fuel injection, exhaust, and interfaces. The installation of the turbocharger and exhaust gas manifold completes the gas exchange system. Finally, the engine is connected to a dynamometer for controlled testing, validating performance, efficiency, and emissions before delivery. At Caterpillar's marine engine manufacturing facility in Kiel, Germany, production is driven by precision engineering and strict quality control. The workflow begins with high-accuracy machining, where major engine components are produced using advanced CNC systems to achieve tight dimensional tolerances. This is followed by rock pouring and extensive testing, ensuring material integrity before components move further down the line. A critical step is plasma valve machining, a process that enhances surface hardness and thermal resistance of valve components exposed to extreme combustion temperatures. Cylinder heads are then machined with careful attention to cooling passages, sealing faces, and combustion geometry to ensure durability and efficiency. In the assembly hall, engines are built in a controlled sequence. Core components such as crankshafts, pistons, fuel injection systems, and turbochargers are installed under defined torque and alignment standards. Final component installation integrates electronic controls, sensors, and auxiliary systems. Each engine undergoes on-site operational testing, where performance, emissions, and reliability are verified under load. Customer inspections take place before approval, after which engines are prepared for transport and shipment, ready for global marine service. The construction of the Quintrex 7600 HT yellowfin plate boat is a highly controlled manufacturing process that highlights precision welding, structural engineering, and durability-focused design. Each hull requires more than 80 hours of welding, reflecting the complexity and strength built into every vessel. The process begins with forming the hull into two symmetrical halves. Heavy-duty aluminum plates are precision-cut, then shaped to create mirror sections of the hull. These halves are carefully aligned and welded together along the keel, forming the solid base of the boat. A 6 mm bottom sheet provides impact resistance and load-bearing strength, while 4 mm side sheets reduce weight without compromising rigidity. Next, internal aluminum plates and frames are assembled and welded to shape the full hull structure. Quintrex's internal Marine Corps rib system is installed at this stage, creating an armored internal skeleton that distributes stress evenly across the hull. This system significantly improves torsional strength and offshore performance. The transom section is then fitted and welded, engineered to handle high-powered outboard engines and repeated dynamic loads. Once the outer shell is complete, attention shifts to the interior. Internal welding inside the hull secures ribs, stringers, and reinforcement points. Structural components, such as side bench seating frames, are welded in place, integrating seating with the hull's load-bearing structure rather than treating it as an add-on. Final welding passes ensure all joints are sealed, aligned, and reinforced. Every weld is inspected for consistency and penetration, ensuring long-term reliability in harsh marine environments. The result is a robust, Australian-built plate boat engineered for strength, safety, and serious offshore use, with construction quality visible in every structural detail. In July 2012, the seventh model in the Superior series entered the water, the Van der Heyden Superior 2000. Measuring 20.7 meters in length with a 5.6 meter beam and a displacement of approximately 45 tons, this yacht combines substantial presence with refined engineering. Powered by twin 825 HP engines, it is capable of reaching speeds of around 25 knots. On board, 4 well-appointed cabins provide accommodation for up to 8 guests, balancing performance with cruising comfort. The Superior 2000 reflects Van der Heyden Yachts' approach to craftsmanship, integrating power, scale, and interior functionality into a cohesive luxury vessel. Making a connection between 2 pipelines while suspended on the open sea is one of the most demanding operations in offshore engineering, where motion, timing, and precision must be perfectly aligned. As the vessels hold position using dynamic positioning systems, the pipe ends rise and fall with the swell, never fully still. Specialized lifting frames and tensioners are deployed to stabilize the pipelines, carefully controlling vertical and lateral movement. Every adjustment is calculated to absorb wave energy while preventing excessive stress on the steel. Surveyors and ROV provide real-time alignment data, guiding crews as the 2 pipe ends are brought within centimeters of each other. Throughout the operation, communication between deck crews and control rooms remains constant. Weather windows are narrow, and any sudden change in sea state can delay the final connection. When the joint is secured and tested, the pipelines become a continuous system beneath the waves. This moment marks not just a technical success, but the culmination of planning, coordination, and control in one of the most unstable environments engineers face. Completed in 1860, the Elbląg Canal in Masuria, Poland, remains one of Europe's most remarkable hydraulic engineering achievements. What distinguishes this waterway is its system of 5 inclined planes, where vessels are transported over land on wheeled cradles, powered by a water-driven hydraulic mechanism. Instead of traditional locks, ships are lifted and carried across elevation changes along rail tracks. Remarkably, much of the original 19th century machinery is still in operation. The canal historically connected towns such as Deutsch, Eylau, Oosterode, and Elbląg with the Frisches Haff, and is known in Polish as Kanał Elbląski. Boats are meant for water, but on Poland's Elbląg Canal, they travel across land. Using a 19th century hydroengineering system of inclined planes, vessels are lifted onto rail-mounted cradles and hauled over hills. 5 such transfers overcome nearly 100 meters of elevation difference before the journey returns to open water.